All right, so we've now seen the rotational analog of kinetic energy. Now, again, there is no rotational analog of gravitational potential energy, since that only depends on where the center of mass is. And again, that center of mass won't rotate. It's usually rotating about that center of mass, so we usually don't have any deviation from there. So the next topic we want to look at is going back to forces. What is the rotational analog of force? And that rotational analog of force is what we call torque. So, as we talked about, back when we talked about forces, what happens is that a force is the analog, or not the analog, but is the generator of linear accelerations. Using that analogy then, what that means then is that torque is actually then the generator of angular accelerations. So what this means then is what caused those angular accelerations that we saw back in chapter 4 is actually torque, which again is this angular analog of force. Now the best way to think about torque, or to see torque, is to look at an example we use with torque every day, which is simply a door. So when we open a door, we're actually using torque. And first things we know is that what torque, which we're going to call tau, this is then proportional to different objects. That first one we can see is what? Torque is going to be dependent on how far away from the pivot point at which this door is going to rotate about, i.e. the hinge. Meaning that if I try to push directly onto the hinge of the door, this door is not going to go anywhere. Unless I, of course, break the door down, knock it off the hinge, and I might get fired if I actually do that. But this means that this thing is not going to move, or at least have a torque to it if I push directly on the hinge. But the other thing I know is that if I start pushing further and further and further away from that hinge with a fixed amount of force, I can generate then more torque based off of how far I am away from it. For example, if I push a certain amount of force onto here, I can cause the door to rotate this much. Whereas if I move further away with the same amount of force, it can actually rotate even further. And finally, if I push near the end of the door with the same amount of force, it will rotate even further. Which tells us then that torque is proportional to, we're going to call that R, where R then is equal to the distance away from the pivot point. So by simply pushing on this door, what I know is that the further and further I am away from the hinge, at least from the hinge or from the pivot point, I can then generate a much greater angular acceleration, i.e. give it a bigger amount of torque. Other thing we know is that if I push a certain distance away, the more that I actually push on this thing, say if I give it this amount of force versus a greater amount of force, I can again cause this thing to actually accelerate faster, causing this to have a much greater torque. So this also tells me that torque is proportional to the force that we're going to apply. The last thing is, if again I want to open this door, what I know is even though I'm going to push away from this hinge, I'm going to give it a certain amount of force, but it depends on how I put this force onto the door. So if I try to open a door by simply applying a force which is parallel to the door, I'm going to be stuck in this room forever. I'm never going to get out. I'm stuck in physics. But if I apply that force somehow perpendicular to the door, so in this case I'm applying the force in this direction, I can then cause a torque causing the door to open, but I can get the greatest amount of torque by simply pushing at this thing at a 90-degree angle. Now, going back to what we talked about when we talked about vectors, cosine always goes with how parallel two objects are, which means sine tells me how perpendicular two objects are to each other, which tells me then that this also must be proportional to sine of the angle between those two objects. So if I put all these pieces together, what this tells me then is that torque is going to be equal to the magnitude of R, where R is going to be a vector which points from the pivot point to where the force is going to act, times the magnitude of the force times sine of the angle between the two. So in this case, R is going to be a vector which points to where the force is actually acting. The force is going to be pushing off into some particular direction. The angle then is the angle specifically between these two vectors. So again, R is a vector which points from the pivot point to where I'm applying net force. So in this case, my pivot point is here, applying the force. R would be a vector which points in this direction. I should probably move my hands. So R would be a vector which points this way to exactly where that force is acting. F would then be the magnitude of the force, and R is the magnitude of that distance vector, and then sine is the angle between those two things. Now, one thing to note about torque, as opposed to, we talked about energy, is that here, torque is actually a vectorial quantity. So I'm getting vector, meaning that the direction of the torque is going to be dependent on how I'm actually applying these things. So if I put all this together, what this finally implies to me then is that torque is actually a vectorial quantity. We're going to say torque is then going to be equal to R cross F. So R cross F, this is then the third way that we can actually multiply vectors together. So as we talked about way back when in chapter 3, what we said was that there are three ways to multiply vectors. First way is multiply a vector by scalar. All that does is rotate the vector by 180 degrees in 2 dimensions, or reflects it through the origin, or rescales the size of that thing. So again, if I multiply by half, it shrinks it by half. Multiply by 2, it doubles the size of it. Second way was the dot product, or the scalar product, where I took two vectors and I multiplied them together to get a scalar quantity. This is the third way, which is what's known as a cross product or a vector product. So here I'm taking two vectors and I'm multiplying in such a way that I get a third vector out of it. So let's spend a little bit of time talking about cross product. So what is a cross product? And let's talk about some properties of a cross product. So let's move this guy this way. Our usual location. There we go. So let's say I have two vectors A and B. So I have vector A and I have vector B. I'm going to do this in component form and non-component form. So this is going to be written as AX in the I hat direction plus AY in the J hat direction plus AZ in the K hat direction, which is then I have BX in the I hat plus BY in the J hat plus BZ in the K hat. And let's kind of schematically draw them over here as well. So let's say this is vector A pointing in this direction, and then this is vector B. So we want to know what is the cross product between these two. So let's consider vector A crossed by vector B. What is this guy? Well, first things first, let's talk about the magnitude of this cross product. So the magnitude of the cross product of vector A crossed by vector B is then equal to the magnitude of A times the magnitude of B times sine of the angle between the two. Exactly the same thing we wrote down for torque. So what does that mean? So ultimately what this means then is that, when we had the dot product, which was magnitude of A times magnitude of B times cosine of the angle between the two, what we said was that physically told me how parallel two vectors were to each other. So again, the way that worked was we dropped a perpendicular onto the one vector, and we said that this distance here was then vector A dotted by vector B, which was telling me how much was vector A parallel to vector B. This guy then, since it goes with the sine, what it actually tells me then is how perpendicular these two vectors are to each other. So the first thing we can learn from this is that what? The magnitude of a cross product tells me then how perpendicular two vectors are to each other. So this is a measure of how perpendicular two vectors are to each other. So in this case, it's a measure of how perpendicular A is to B and how perpendicular B is to A. Now, this goes back again to our torque, which says that what? We get no torque. I can't open the door if I push, in this case, parallel to the direction of the door. Now, in that case, what would happen then is that the R vector would point this way, your F vector would point this way. So in this case, I would have sine of 0 degrees, which would give me 0 torque. Or if I applied the force in the opposite direction, in that case, I would have R vector is this way, F is this way, that'd be 180 degrees. Sine of 180 degrees is so simply equal to 0. Now, what are some other properties of this guy? So other properties of this are, what happens then is if I take these two vectors and I cross them with each other, that actually gives me a third vector. That third vector, let's call that vector C, is defined then as vector A crossed by vector B. Now, the way I determine the direction of vector C is we're going to use what's known as the right hand rule. So what does the right hand rule say? So it says step number 1, point fingers in direction of vector A, of first vector. So in this case, that's going to be vector A. Step number 2, curl fingers toward second vector, which in this case is going to be vector B. Now, we don't just curl them in any old direction. What we do is we curl them in the direction of the smallest angle. Step number 3, thumb, which is perpendicular to the hand, points in direction of the result, which in this case would be vector C. So what does this mean? So let's look at this example. So here, I pull my fingers in the direction of vector A, curl them towards vector B in the direction of the smallest angle, which means I'd have to rotate my palm in the direction of vector B, curl my fingers then towards B, and then my thumb, which is at a 90-degree angle from my hand, points in the direction of vector C. So in this case, vector C would actually be pointing into the board. So this is then our cross product. Now, notice one other property about cross products is what happens if I did this in the opposite order. Now, we talked about with dot products, we know is if I took vector A dotted by vector B and I took vector B dotted by vector A, that's exactly the same thing. But here, as we can see, this is actually no longer the case. So if I instead did vector B crossed by vector A, so in this case, I would put my fingers in the direction of B, curl in the direction of A, so I'd have to rotate my palm up, so I could curl in the direction of A. My thumb, again, would point in the same direction as vector C, which in this case would be going out of the board instead of into the board. So another property of vectors here, at least of the cross products, is that A crossed by B is not equal to B crossed by A. In fact, it's actually equal to negative of B cross A. So when it comes to cross products, the order at which I actually do this cross product is important. So I can't just arbitrarily cross them in a particular way. I have to cross them in the way at which this is specifically telling me to do so. So always do the first vector crossed by the second vector, and then your thumb gives the direction of the third vector. So the second property in this case is that what? The order at which this thing matters. So if I did the opposite order, I get exactly the same magnitude, because the magnitude of this doesn't matter, but I get actually the wrong direction. So I would get the wrong direction of vector C in this case. Now, using this fact, this also tells me that going back to here, that a third property is that what? This magnitude of this cross product is actually the same thing as the area of what's known as this bivector. So if I put A, B here, and then A here, so actually the area which is generated inside of this region is actually equal to this cross product. So the magnitude of A cross B is then equal to the area which is created by these two vectors. So in this case, magnitude of A cross B is the area generated by the two vectors. Now, the last property we're going to talk about is something about vector C. So it turns out that vector C is actually perpendicular to both vectors A and B simultaneously. So let's draw a slightly different picture. Let's see how that works. So let's say that vector A was actually pointing off in this direction. Vector B was pointing off in this direction. So what I mean by A is it's kind of pointing out in this direction. So what's going to happen then is if I put A in this direction, B is here, I curl my fingers in this direction, which means vector C would be a vector which would point off in this direction. And what happens is actually vector C is perpendicular to both A and B simultaneously. So here we have C is perpendicular to A and C is perpendicular to B. So what actually happens then is that this area here defines a plane, and vector C then is perpendicular to that plane at which this is defined. So vector A points this way, vector B points this way. Put my fingers in the direction of A, curl towards B. My thumb would be pointing in this direction. So these vectors A and B would define a plane, and then vector C would point perpendicular to that plane. So this is a cross product. So this is the magnitude of the cross product, but what about in component form? So again, if I have vector A and vector B in component form, we want to know what vector would that give me in terms of vector C. So we want to consider then what is vector C, which is equal to A cross B. Well, the way we do this is we determine, or we use what's known as a determinant. So here, I'm going to write out what's called a matrix. So in the first row of the matrix, I'm going to write out the unit vectors, I, J, and K. Underneath that, in the second row, I'm going to put all the components of vector A. So this is the components of vector A. And then below that, I'm finally going to put all the components of vector B. Oops. And then I'm going to take what's called the determinant. So the way the determinant works is the first thing we're going to do is we're going to cross off this row and cross off this column and take whatever entry this is and then multiply by what's known as the minor determinant. So this is going to be equal to then I times. So the way the minor works is I'm going to take this times this minus this times this. So that means I'm going to get an AY minus, or times BZ minus AZ times BY. So now that I've done that, I'm now going to take the next, which is I'm going to cross off exactly the same row, but now I'm going to cross off the next column. Now, don't worry too much about why this is true, but for this one, we have to multiply by -1. So I'm going to multiply by -j instead of just j. So now I'm going to do exactly the same thing. Look at the minor matrix. So I'm going to take this guy times this guy minus this guy times this guy. So this is now going to give me AX BZ minus AZ times BX. So finally, now that I have that guy, we're going to do exactly the same thing. I'm going to cross off exactly the same row, cross off now the final column, and now multiply by this guy. So this one becomes another plus, so then I get plus K times, and again, let's consider the minor matrix. So again, this guy times this guy minus this guy times this guy. So I get an AX times BY minus AY times BX. So this is what's known as the cross product in component form. Now, for the purposes of the class, if you don't quite understand what happened here, don't worry about it. You'll see it again when you take multivariable calculus. But for now, just note that if you're dealing with something in component form, this is actually the definition of the cross product. So all this says to me then is that what? Since vector C is written also in component form, so I can rewrite this then as what? Cx in the I hat direction plus Cy in the j hat direction plus Zz in the k hat direction. What has to be true then is that this component here must be equal to the same component over here because the i's must be in the same direction. So if I put that together, what this says then is that Cx must be equal to Ay times Bz minus then Az times By. Cy then must be equal to Az times Bx minus Ax times Bz. And then finally Cz would be equal to Ax times By minus Ay times Bx. So these are the components of the resulting vector based off of this cross product. Now again, what does a cross product mean? Again, what it tells me literally is how perpendicular our two vectors are to each other. It tells me the area of the triangle, or the area of this diamond, which is created by these two vectors that I'm crossing together, and that vector c is perpendicular to both vector A and vector B simultaneously, which means that it's perpendicular to the plane which is created by vectors A and B. Now, let's go back to torque. So torque, we now know, is equal to vector r crossed by vector f. So what this says then, again, is that we have to cross vector r crossed by vector f, where again, r is the vector which points from the pivot point to where the force is acting, cross that by the force, and then our thumb, again, right hand, not left hand, make sure it's right hand, points in the direction of the torque. Now, again, if I do this in opposite order, I have the force in exactly, or the torque in the wrong direction. So how does this apply to something that you know? So what you know is something like a screwdriver. So we've all been told, since we're young kids, righty-tighty, lefty-loosey. So what that means is we turn in the right direction to tighten the screw, we turn in the left direction to untighten the screw. Why is that? Well, that comes from this expression. So here, imagine this is my screwdriver. What I'm going to be doing is rotating about the center line of this, which means that I'm applying the force parallel to the surface here, or tangential to the circle which is created, and then my r vector is going to be the vector which points from the center, which is where I'm rotating about, to where that force is acting. So in this case, if I'm doing righty-tighty, my force is going towards you in this direction. R is going to be here, so if we use this, we point our fingers in the direction of R, curl towards F, which is in this direction, so our thumb points in the direction of the torque, which means as I'm doing righty-tighty, the direction of my force, or my torque, is in this direction. So your screw is being driven in the direction of the torque. Now when I do lefty-loosey, in this case I'm rotating my hand in this direction, which means I'm applying the force towards me. So in that case, I put my fingers in the direction of R, but now I have to curl them towards F. So rotate my palm to myself, curl towards F. My thumb now points in this direction, so when I do lefty-loosey, the screw is now being driven out in the direction of the torque. So this is how we understand what torque is. Now, as far as this class is concerned, all of that is great. This is good information. I'm mostly telling you this because next semester we're going to be considering magnetism, and everything is defined in terms of cross products and magnetism. But for now, all we really care about is how does a force rotate an object. So even though all this is great, let's kind of ignore it for now. So what I really care about is if I apply a force to an object, let's say here is my object, and I apply a force to it here, if that causes my object to rotate this way, meaning in the counterclockwise direction, we're going to call that guy a positive torque. If my force is instead applied in this direction, which causes it to rotate in the clockwise direction, I'm going to call that guy a negative torque. So for our purposes, all we really care about is how does this guy move? So if this is my pivot point, apply a force in this direction, it rotates in the counterclockwise direction, that's then going to be a positive torque. If I apply my force down in this direction, rotates in the clockwise direction, that's going to be a negative torque. So as far as this class is concerned, that's all we really care about. How does this thing rotate? Is it going to rotate counterclockwise or clockwise? And here, don't worry too much about all the specifics. It will become important next semester, but for this semester, don't worry too much about that. So this is torque. So again, torque is the rotational analog of force. So let's go back to our replacement scheme. So again, our replacement scheme said that x goes to theta, v goes to omega, a goes to alpha, m goes to I, so again, mass goes to moment of inertia. And now our next piece is going to be that force goes to torque, this tau. So what does that do to Newton's second law? So let's remind ourselves of Newton's second law. So Newton's second law, in the form that we know it, says that sum of the forces is equal to the mass times the acceleration, which means that, using our replacement scheme here, mass now goes to the moment of inertia, acceleration now goes to the angular acceleration, and the force now goes to torque. So the angular analog of Newton's second law now says that the sum of the torques acting on the object then is equal to the moment of inertia times then the angular acceleration. Now, some things to point out here. First of all, just like mass here, which is always a positive quantity, moment of inertia is always a positive quantity, which tells us then that the net direction of the net torque will always be in the direction of the angular acceleration, or the direction of the angular acceleration will always be in the direction of the net torque. So again, as we said earlier, all this tells me then is, again, Newton's second law says that force then is what generates linear acceleration. So angular acceleration then is what generates, or torque is what generates angular acceleration. So to get something to move in an angular fashion, has this guy do that, what is actually generating the angular acceleration as this thing is falling down is in fact torque. So torque in this case is due to the fact that this thing has a mass, i.e. has a center of mass. Gravity's pulling down on the center of mass, so as this thing swings down, it's actually gravity which is generating the torque due to the fact that I have a pivot point here. As opposed to if I simply drop it, there is no rotation, because in that case there is no pivot point, so this thing is not going to rotate about. It's simply going to fall linearly as Newton's second law. But as soon as I have a pivot point somewhere, say again the end of this rod, the angular acceleration which is generated is then going to be dependent on this pivot point and will be due to the fact that this thing has a torque. Now, okay, other things to note is, just like mass, again, if mass increases, the angular acceleration decreases based off of the force. Same thing is true here. So if I have a bigger moment of inertia, then the angular acceleration must be decreased based off of the same amount of torque. So again, this is torque. So torque is simply the generator of angular accelerations. Just like force is the generator of linear accelerations. So next time we'll see some examples of this guy.